possibly the greatest of all the American violinists, or possibly even, I may be sticking my neck out, the greatest violinist of the last century was Isaac Stern. Any strings people who want to object? I could be wrong. Isaac Stern was once asked how he manages, or how he managed, because he is no longer with us, to be so absolutely spot on in his intonation that every note was perfectly in tune. And he answered, according to the story, every note is wrong, and then I corrected very quickly. There probably was some truth to this. I don't know whether you have any interest in this kind of thing, but why did I even mention it? Well, I make lots of mistakes. Fortunately, I have Jonathan Lewin right at hand. He says, "Lewin, what the hell are you doing? How can you do this? What do you mean by delta?" You know, I do the same thing to me that I would do to anybody else. Well, I didn't catch myself quite as quickly, and I let you see an error. Last time I lectured, I realized it was happening as I did it, and I didn't want to slow the lecture down. And so instead of correcting it in the lecture and wasting time, I made a separate video. Have you noticed it and opened it in that problem? And this is hopefully correct here. Okay? The lecture notes from the CD from last time may not be correct there, but from the website should be correct. Also, in any CD from today on, the lecture from that time should also be correct. Okay? And am I proud? No, I make mistakes as well. Even Isaac Stern made mistakes with his playing, although personally, with the level of talent that I have, I never heard any of them. It sounded absolutely perfect to me. So what can I say? Now, you want to hear Lewin playing the violin? I think, something like Colonel Klink, if you know, right? So, all right, enough of that. My intonation is not good. My bowing was quite good when I tried to play, but my intonation stunk. So anyway, I actually got a nice tone, but the wrong note. So anyway, until my teacher kicked me out. He said, "You are my worst pupil. Begone." Right. So, folks, we've been talking about limit points, and I'm going to give you a quick review, and then we're going to do a repeat of the problem at the end of the last lecture, and this time we're going to do it better. We're going to do it a little more deeply than before. So, when do we call a number a limit point of a set? You've got to be so careful, get the language right. I had people telling me, this number is an upper bound of that number. Or this set is an upper bound of that set. Excuse me. You better get the words right, folks. I'm not going to nag anymore. I've dealt with these things as they came to the extent that I could. Right. When do we call a number a limit point of a given set? A number is called a limit point of a set when the number is close, not merely to the set, but even to a slightly smaller set. What smaller set? The set you get by striking that number out. In order for a number to be a limit point of a set A, in other words, to belong to the set that I write L of A, and if you look in the textbook, it's a nice curly L, created for me, the calligraphic screen style created for me by a student of mine by the name of Dylan Simonton. And he made this for me. He was really very good at doing this. but then he stopped doing math and left me. So anyway, but I couldn't put that into your lecture notes. So you've got a plain, ordinary, bare bones L here. L for Lewin, L for limit point, L for limit point. Okay? What does it take for a number to be a limit point of a set A? A number X is a limit point of A when the number is close to that set. Of course, any such number will be close to A. If a number is close to a set, it'll be close to any set that includes the given set. So there's no question that every limit point of a set is close to the set. I also gave you examples like this. That's why I've left it in the lecture notes. The number 5 belongs to that set over there. But it's not a limit point. Because I can give you an example to prove the existence. How do you prove existence? God, I asked you in this test. I said, how would you prove that a set is not empty? The answer is you find an example. You give an example of a member. You don't choose. Lots of people telling me choose. You can't do that. You choose after you know that a set's non-empty. You use the known existence. Anyway, but I can give you an example of a positive number delta such that the stick center 5 radius delta doesn't touch any of that red stuff over there. It's easy. Try delta equals 1 or anything smaller will be fine. So therefore, 5 is not a limit point of the set here, because if you strike 5 out of that set, what remains, 5 is not close to what remains. You see? A number x is said to be a limit point of a set A when the number x is close to A slash singleton x. Now let's spell it out. What does it mean when we say a number is close to a set? It means that for every delta greater than 0, the stick center x radius delta intersects with the given set. Okay? The statement that a number x is a limit point of a set A is the statement that for every delta greater than 0, this intersection is non-empty. Meaning what? There must exist at least one number that belongs to that interval and that belongs to A and is not equal to the given number x. Do you understand? There must exist a number other than x itself, about which I do not care or know. Other than x itself, there must be at least one other number that belongs to the interval and belongs to A. That's the condition. That's what I wrote here.
So any interior point not equal to x would be
let's not talk about an interior point of a set would always be a limit point, but I don't want to do that now. Then I said, what if a number fails to belong to a given set? You see, that's not over here. 5 belong to the given set, you see. What if a number x does not belong to A? If the number x does not belong to A, then A slash singleton x, what does this mean? A slash. By the way, this sign can be made from the toolbars. It's a binary operation. You can find it among the binary operations in the toolbars. But it's called set minus. That's its name. It's the set subtraction. And you can make it by holding the control key down and typing SET-MINUS. If you have put in my fragments, how many people have bothered to do that? Few people. If you've bothered to put my fragments, you can make it with DF for distance, for difference. DF is a shortcut, it's the one I use. Anyway, just thought I'd mention. Anyway, if x does not belong to A, that's what I'm looking at. Suppose x does not belong to A. Where am I? Here. Then A slash singleton X, which means the set of all those members of A that are unequal to X. Well, if X doesn't belong to A, then this is redundant. You understand? Because X wasn't there. I mean, suppose I said the set of all people in this room who are not the President of the United States. That's the set of all people in this room, I think. Get me worried, right? Okay? So, yes. Don't look at me, I don't qualify. The Constitution of the US says you've got to be a born citizen. Those of us who are naturalized are second class. Okay. So the fact is that these two sets are the same thing. So the statement that for every delta greater than 0, this is non-empty, is exactly the same as the statement that this is non-empty for every delta greater than 0. You understand? So I told you last time that when a number doesn't actually belong to the set, the condition of being a limit point of the set is precisely the same as the condition of being close to the set. Okay? Now let's talk about this equation. When a number belongs to a set, it is definitely close to the set. Isn't that right? And every limit point of a set, I've already told you, limit point's harder. Definitely close to the set. Now we've got to do the other direction. This is a bit harder. It's no longer here. I did it last time. This is review. That's why I'm not doing this very carefully. Suppose that you take a point in the left side. It either does or does not belong to A. If it does belong to A, it's on the right side. If it doesn't belong to A, then the condition of being close to A is precisely the same as the condition of being a limit point. So if we're close to A, it's a limit point. You understand now why these two things are equal to each other? We already know from an earlier life that a set A is closed if and only if A equals A bar. You understand that when you're studying limit points, you jolly well have to be completely up to date on closure. You have to be able to, every definition, everything we ever wrote, you have to be able to just rattle it off. If I say Mary had a little, you know, you might think, well, I think it was a rhinoceros, okay? You have to, everything has to be completely fluent and smooth on the earlier material, okay? Folks, I can't see all your eyes. You should be doing nothing other than concentrating on what I'm saying. And that means nothing else, okay? Electronic devices, looking at books, okay? You need to be concentrating. What I'm saying is that a set is closed when its closure equals itself, if and only if. So a set is closed if and only if. What happened to the bar here? Oh, it's there. I'm looking at the wrong line. A set is closed if and only if this is A, right? Well, when this is A, the equation says that, okay? And this equation says what? When A equals A union some other stuff, then the other stuff has to be a subset of A. To cut a long story short, I explained to you that that a set is closed if and only if every limit point belongs to the set. I've just done one direction for you. You want to see the other direction? What if you know that this is a subset of A? And this is A. And that's a subset of A. So the union is A. But that's A bar. Therefore, A equals A bar. Therefore, A is closed. Okay? All of this was done last time, and I've just been reviewing. Now we're going to be doing the following. What can we find in a neighborhood of a limit point of a set? And to answer that question, I need coffee. Excuse me. Before my Calc 2 students come in, they will help themselves. I've got to finish with an empty thermos, and they help me do that. You were also welcome, by the way, as a general invitation. I'm not going to say it every time. Right, here we go. I put in a little paste in here, and I'm just letting you know that the question I'm answering appears as 665 in the text. Okay? You can get this either from the printed version or on screen. Now, we are assuming that x is a limit point of a set and that delta is greater than 0, and I want to ask a question. What can we find in that stick? What can we find in a neighborhood? Here's a little stick neighborhood of x. What can we find? And I'm proposing something. I'm saying, let's suppose that we have identified some numbers called x1, x2, x3 up to xn. That's how many numbers have I got here? Can you count? There are n numbers there that happen to belong to that stick and belong to the given set, which I've called E, and are unequal to x. You understand? I'm saying let's make the supposition that these numbers all belong here. And I'm going to show you that these numbers cannot possibly be all the numbers in there. Now this n might have been 55. It might have been 55 million. I don't care. I'm saying that in the event that you take finitely many numbers, which I might as well call x1 through x17, or x1 through whatever, however many you got. I called it n because I don't want to commit myself to 17 of them, you see. Last time, by the way, I did commit myself. I took one number. Now I'm just being a bit more ambitious. I'm saying, let's suppose we have finitely many numbers called x1, x2, x3 up to xn, n numbers that happen to belong to the stick center x radius delta for a certain positive number delta and belong to the set E, and none of them are equal to x. And I'm going to demonstrate to you in just a second. I'm going to show you that in addition to those numbers, I'm going to find another number. Other than all these, I'm going to find a new one, Harry, that will, a new boy comes in and is going to be, would you rather Harry yet? So I don't get into trouble here. It comes in belonging here other than these. That's what I'm going to show you. If you ever take finitely many numbers that belong here for delta greater than 0, assuming that x is a what? Assuming that x is a limit point of E, then I'm going to show you that these are not all. These are not all the numbers that can belong here. Right. Proof. Well, what color should we make it? Yellow? Right. Here we go. We define delta. Now, if I define delta, I'm going to tell you exactly what I mean by delta. You understand? I'm not choosing. Okay? I'm telling you exactly. We define delta to be 3. Except that that's a useless definition. You see? But that'd be a perfectly grammatical to say we define delta equals 3. It's sort of like driving your car, stopping at the stop streets, keeping on the correct side of the road, obeying the speed limit, driving the correct way in one-way streets, and being totally lost in the city. You see, you won't get a ticket, but you are not happy. you see.
You're getting it.
So I'm not going to do, we define delta equals 3. Excuse me, that's useless. We define delta to be the smallest of the numbers absolute x minus x1. Whoops. I can't call it delta. You can't do that. There's a symbol delta in use here, isn't there? You better use a different symbol. What should we use? I don't care what you call it. You just can't call it delta. See? You can call it Rumpelstiltskin if you like, as long as the problem never stated a Rumpelstiltskin. Anyway, we define, all right, epsilon. It's about time I introduced you to a few more Greek letters. Some of you have such trouble making Greek letters. Get people who are using the partial sign for the Greek letter delta. Let me give you a little bit of information, which you would know in any case if you had bothered to run my workshop that I gave you. But if you want a Greek letter, if you do Control G, the next one key you type will be Greek. It's the quickest and easiest way to make delta. The D obviously give you delta. You want to know how else you could make delta? Hold Control and type DELTA. Okay? If you hold Control and you type United Airlines, it will not give you a delta. Okay? So you just have to do it right. So, all right, we define epsilon to be the smallest of the numbers. Absolute x minus x1 and absolute x minus x2 and absolute all the way up to absolute x minus x n. See?
You meant to write x minus x2 for the second.
Ooh, I did. I said a 2 and I wrote a 1. Okay? Isaac Stern, I am not. Okay, we define epsilon to be the smallest of all these numbers. Please note that this epsilon cannot be more than the number delta. Because, you know, I said that these numbers, x1, x2, x3, up to xn, where do they all live? In here, right? The distance from x1 to the center x is actually less than delta. And the distance from x2 to x is less than delta. Every one of these is less than delta. I can tell you even something better. I can even tell you a less than. I wasn't lying when I said less than or equals. You know, if it is perfectly true that 2 is less than or equal to 1,000,000. That's true. Okay. It is perfectly true that I'm not richer than Bill Gates. The fact that a stronger theorem is available. Okay. Now, this number epsilon is not more than delta. It's actually less. Okay? And we can see that the interval center x radius epsilon is a subset of that. Do you understand? Because epsilon not more than delta. Right. I would like to mention to you that this set here, our set was called E. That set must be non-empty. Isn't that right? Because x is a what? A limit point of E. And epsilon is what kind of number? It's the smallest of finitely many positive numbers. It's one of them, definitely positive. Okay? That set must be non-empty. Okay. Choose a number, what should we call it? Bugs Bunny or something. Y, all right. In here. And note that definitely Y belongs to that bigger, whoops, choose a Y. I've lost my stupid epsilon. The epsilon is positive. I'm trying to tell you that the set must be non-empty because this number is positive. It's one of these positive numbers. Okay? So therefore, this must be non-empty. And I'm going to say choose a number Y that belongs here. You understand? We can see that definitely Y belongs to the original intersection because Y belongs to that smaller interval. It definitely belongs to the bigger one. You see? And it belongs to E and is unequal to X. So we have found and Y is none of the numbers x1, x2, up to xn. You see? It's none of those numbers. Why? How do you know? Because the distance from Y to X is less than the least of the distances from these guys to X. If you're less than the least, you're not one of them, right? You sell your BMW somewhere else, okay? So that is basically the story. Will you study this, please? It's a little bit tricky. So I want to tell you, we can make a conclusion here. Actually, the set, this set must be infinite. It can't have only finitely many numbers in it. Because however, if you take finitely many numbers in here, you can always find another one. So could there have been only 23 numbers? Because I can find you another one. So okay, could there be only 24? I can find another one.
So
you
it's
see?
either empty or infinite.
So no, it can't be empty. I'm assuming that delta is greater than 0 and that x is a limit point of E. There's no way this can be empty and there's no way it can be finite. You understand? So, so I want to tell you that if you ever take a neighborhood of a limit point of a set, not only are you guaranteed a member of the set in there other than your point, there must be infinitely many different numbers like that. A neighborhood of a limit point of a set must contain infinitely many different members of the set. Okay? I'm going to make two little applications of that. The first one is this, which should have been done first. So let's put it over here. I'm trying to get you over there. Right. Finite sets don't have limit points. If you have a finite set, there's no way that it can have a limit point. Why? Well, take a finite set called Charlie. Now, take a point x. Can x be a limit point of Charlie? Well, take the interval center x radius 5 or 2 or whatever some positive number and intersect with Charlie. Can that be infinite? I told you Charlie was a finite set. If you take a stick around a number x and you intersect with Charlie, can that be an infinite set? There's no way. Therefore, the point can't be a limit point. Because if you take a neighborhood of a limit point, we can find infinitely many different members of the set in that neighborhood. You see? And therefore, a finite set never has any limit points. I'm now going to ask you a question that I won't answer. What about every infinite set? I've just told you that a finite set never has limit points. Maybe there'll be a theorem every infinite set must have limit points. What is your intuition? How many votes? How many people say yes? Every infinite set must. Please get the votes. I've got 2 votes, 3. Do I hear more? Who says no? Lewin is going to come up with a sneaky example of an infinite set that doesn't have any limit points. We've got 1 vote. 2, you didn't vote twice? Right? I'm just teasing. And the answer to the question is, I ain't telling. I'm not going to tell you. But I am going to do this one over here, and then I'll answer the question. All right, I'll answer the question. Talk to me.
Integers.
Make it, yeah. Tell me.
Set of integers is infinite but has no
Yes.
doesn't have any integers.
The set Z of all integers is infinite, but you know what but means? It means and. There is no logical difference between the words but and and. But suggests that you weren't going to expect this, you see, but otherwise it just means and. It's infinite but has no limit point. Now, I need a quick proof. Why does the set Z have no limit point? Here is the proof. Suppose that x is a number. I want to show that x must fail to be a limit point of Z.
Do you want to say number or integer?
Any number. Because I want to say that Z has no limit point. I don't want to merely prove that no integer is a limit point. I want to prove that no number whatsoever can be a limit point. So I'm saying suppose that x is a real number. Okay? I must show, okay? Right. Please note that there are not infinitely many members of Z in the interval center x radius 3, 2, 1. What should we put? 7? Anything you like. How many integers can be in there? Maybe 1, maybe 2. Could it be 3? Makes my head hurt. I can't. Not infinitely many, right? Therefore, there is no chance that x can be a limit point of Z. Reasonable? Can't be a limit point, because when a number is a limit point of a set, what do you know? A neighborhood must contain infinitely many members of the set. You see? The definition requires that every neighborhood contains at least one member of the set other than your given number. But when that happens, every neighborhood will actually contain a whole bunch of members of the set, infinitely many. You see? Well, there's no way that this little stick around the given number x that I introduced here with suppose, there's no way that this stick can contain infinitely many integers. So I don't have to break my head worrying about, coming in close and leaving out the nearest integer. You don't have to do that. If you want to, you can. You can write a proof like that. The lazy way, it can't be infinitely many integers. They're finished. See? Very quick, easy proof. Right. So therefore, we have no theorem that say, wouldn't it have been lovely? A set is infinite if and only if it has a limit point. Wrong. A set is certainly infinite if it has a limit point. Okay? Please listen carefully to me. If statements are really good in headings, do not use them while you're writing proofs. You will very seldom see me use an if-then statement in my writing. It makes the writing harder. Okay? You will very, very seldom, in fact never, see me write implication statements when I'm writing a proof. I keep them away because I know that you are not capable of using them correctly. 99% of instructors and 100% of students use implication symbols incorrectly. An implication symbol can never be used to arrive at a conclusion. You arrive at a conclusion by saying, I have certain information. From this information, I conclude that. That's therefore. It's a new sentence. An implication. This implies that. Does not say that anything is true. It says, if this is true, then that is true. If-then statements are dangerous. Beware. That's why I've been writing very carefully for you and making you use my notes so that I get you out of bad habits. Bad habits that who knows where you picked up. And they're all wrong and I'm right. Okay. Now, I want to tell you, when you write mathematics correctly, you make it easier. And there's much too much sloppy writing. Makes the subject harder. Make you do it right. Okay. So what I'm saying is, if a set has a limit point, then it must be infinite. But I didn't say that if a set is infinite, there must have a limit point. Okay? Those I'm stating as headings, as statements, not as part of the proof. Notice I wrote much shorter sentences using suppose and pausing and resting. That's how you make it easier. So what's wrong with a set of integers? You can get infinitely many members, but you have to go for a long, long walk to get them, you see. So let's pose a question to you that you will not find in today's notes. What about, what is the question I should be asking? The set of integers doesn't have a limit point in spite of the fact that it is infinite. Well, sad luck, right? Well, then what about, somebody want to ask the question? Nah, it's not the question. No, it's not the question. So the set, of course the set of rationals has a limit point, but I'm looking for a principle. We asked a question, must every infinite set have a limit point? And the set of integers gave what we call a counter example. You see? The set of integers fails to have a limit point even though it is infinite. Okay? Well, what about, what is the question? There's a question that you should be, what about? Someone? Okay, when a question, must every infinite set have a limit point? Finite sets, no. ever, right? Must every infinite set have a limit point? Unfortunately, no, because we have the example of the set of integers didn't have a limit point. We say, well, what about...
Other conditions to make it true.
talk to me.
I mean, being closed, but no.
No, the set of integers is closed. Not good enough. Someone?
Must have been
I'm dying to wheedle this out of somebody. An open set, that's what Julie asked earlier, and I didn't answer her, and I'm not answering you now. Open sets, non-empty open sets always have limit points. I'll tell you later. But I want something that would relate directly to this. Must every infinite set have a limit point? Unfortunately, it doesn't always have to have a limit point, because look at the set of integers. But in order to get infinitely many, you have to go a long, long way. So then you might say, well, what about?
infinite sets with interior points.
Yeah, but that's, yes, sir.
What about like a set with an irrational number as its endpoint?
But what is meant by an endpoint of a set? And why pick on an irrational? I mean, irrational's irrational. I'm trying to get this out of somebody. Well, there's a question that is begging to be asked here. I said, must every infinite set have a limit point? And the answer is, unfortunately, no. Because we have an example of an infinite set that doesn't have a limit point. And you say, well, I wonder, what about... Huh? No, well, finite sets never have limit points. And what might be added to the word infinite? That's interesting. I will mention, because I've got a few people who are aware of countability, an uncountable set will always have a limit point. I'm not going there. That is a special case of something really profound. It can be extended to general topology. You talk about things called separable normal spaces. I would love to tell you about this. It's not coming in this course. Now, infinite by itself is not good enough to guarantee a limit point.
So it's a question of
What would you like to add to infinite that might...
A set contain at least one infinite set that might have an infinite point.
Well, I want to talk about, is it true that every infinite set that is also will have a limit point? Yeah, that's as far as I'll take it.
closed.
Bounded. Closed is no good. The set of integers is closed. Bounded. That's a good question. And I'm not going to answer you.
I just came up with
What do you feel intuitively? What if the set's got an upper bound and a lower bound? It's bounded. An infinite bounded set. What about that? The set of integers doesn't count, right?
positive integers.
The axiom of completeness tells us that if we have a number where every other number in the set is lesser or equal to that number, then we're going to have
Yeah, well, the axiom of completeness will give you a supremum and an infimum, but we're talking about limit points here.
Set of positive integers is bounded below, and it still doesn't have limit.
But what if a set is bounded? Bounded means bounded above and below. What's your intuition? What's your intuition? I'm about to give you a sneaky example of an infinite bounded set that has no limit point, or I'm going to give you one day a theorem that will say that every infinite bounded set must have a limit point. Talk to me.
Would the bounded set be a smaller part of the matrix?
I'm not following you. The question is, do you believe that if a set is both bounded and infinite, that should guarantee a limit point, or do you think I'm about to give you a sneaky example of a set that is bounded in infinite and has no limit point? Yes, sir.
Well, couldn't we find on a delta such as in the interior point, it will fail?
No, listen, interior, forget. I mean, the set, not every set's got interior points. I agree, if a set's got interior points, it's too easy. There could be sneaky sets that don't have interior points. So I'm saying, if you know that a set is not only infinite, but it's also bounded, which means that the set of integers doesn't qualify, right? Do you believe that that set has to have limit points, or do you think I've got another sneaky example, more interesting than this example? Who thinks that I'm going to come up with a cute example of a set that is both bounded and infinite and has no limit point? Let's see how many people think Lewin's about to produce that example. Those are the people who have a negative view of this, right? Who has a positive view? Who thinks that there's going to be a theorem that will say every bounded infinite set must have a limit point? Who feels that? Most people aren't voting, but I've got slightly more than who believe that. Well, I will put you out of your misery. No, I won't. I shall leave you waiting. I'm not going to answer the question today, but I'll tell you what the answer is.
Wait, what? You'll give us the answer, but
But not the answer. Yes.
not how it works.
If I haven't told you how it works, you don't know the answer, right? There's a theorem which is most often known as the Bolzano-Weierstrass theorem that says that in the line, every bounded infinite set must have at least one limit point. I didn't say that there has to be a limit point belonging to the set. I said that it has to have at least one limit point. That's called the Bolzano-Weierstrass theorem. And anyway, are we going to see it now? Hell no, right? Okay. I do want to prove here that the set of limit points of any set must be closed. Must be closed. Here we go. We suppose that S is a set of real numbers. We want to prove that L of S is closed. We want to prove, it's easier for me to prove that, you know what I'm about to write? Complement
The complement is open.
of L of S is open. Whoops. Okay? How do you prove that a set is open? You've got to know the definition. If you don't know the definition, you can't write the proof. A set is called open when what? When? I've got to hear a word. A set is called open when every member is an interior point. Well, I've got a proof for every. What is the next word in the proof? Suppose. Some of you are slavishly writing supposes all over the place without knowing why. You say, I think I better put a suppose. Lewin might, he likes suppose, he'll be happy, right? You've got to have a reason for everything you're writing. I want to prove that every member of this set does something. Suppose that X belongs here. What did I do? Suppose that X belongs here, right? What do I know about X? We know that X is not a limit point of S. Right. Sometimes when I'm dissecting my thoughts, I write very short lines. I'm holding shift and typing shift enter will force me to a new line. It helps you marshal your thoughts. You don't have to. Okay, I'm going to ask myself a question. What do I know when I know that a number fails to be a limit point of a set?
It's not close to the set.
It might be.
Oh, right.
It might be close. It might belong. I know that there exists a neighborhood that
Does not intersect with that.
that does not except possibly at. Right. So when you know that something exists, choose. Don't just tell me that something exists. Use the existence. Get your hands on one of these things if you need one. Choose delta greater than 0 such that if you take the stick center x radius delta and intersect, what's the set called? S, and strike out the point x, you will get nothing left. This thing will be empty. Okay? Now I'm going to tell you something very interesting. Given any number y in that stick, we know that this stick is a neighborhood of y, is it not? And that if you take that stick and intersect it with S, that has only finitely many members, actually not more than one. There's only one number that might belong here. That's x, and I do not know whether x does or does not belong here. But other than x, there's nothing, right? Therefore, this set is not infinite. It is empty, and it may have one number in it, but it doesn't have infinitely many. It doesn't even have two, you see? So I want to tell you something. For every y in this stick, we can see that y fails to be a limit point of S. Isn't that true? I said, given any number y in here, that stick is a neighborhood of y. We know an open interval is always a neighborhood of every number in it. It's a neighborhood of y. And that neighborhood of y does not manage to contain infinitely many different members of S. Does not, you see? And therefore, y has no chance of being a limit point of S, because if you got a number and if you are in possession of a neighborhood of your number that does not manage to contain infinitely many members of the set, your number does not qualify, doesn't get the job of limit point, you see? And therefore, so I'm just telling you, we have an aha moment. Aha. I'm trying to get an exclamation mark. We can see that this stick is included in there. No members of that stick can be limit points of S. Haven't I just shown you that the set is open? Follow the proof here. I'm saying suppose that x belongs here. Why did I write that? Think to yourself, I want to prove that Charlie is open. Okay? How do you prove that a set is open? You've got to prove that every member of the set is an interior point. Suppose that x is a member. What is the strategy for proving that every member of a set eats ice cream? Suppose that x is a member of the set. Period. Don't write anything about ice cream, for heaven's sake. Suppose that x belongs to that set. Now, using the information that x is not a limit point of S, choose delta greater than 0 such that this set is empty. I'm using the definition. How many members of S can be in this interval? The answer is maybe one, maybe none, okay? Because other than the number x, there are no others. Therefore, there's maybe x itself and maybe nothing, okay? So can this set be infinite? No, it can't even have more than one number in it, and maybe not even that, see? So I will say to you that I am in possession of a neighborhood if y belongs to that interval. I'm in possession of a neighborhood of y, a neighborhood that does not intersect with S at more than maybe 1 point, or not even that, but not infinitely many. So therefore, no member of that interval has any chance of being a limit point of S. This interval is included there. And that is what we needed to do to prove that our number that we supposed over here is an interior point of that set. That therefore the set is open because every member is an interior point.
And because that one's open, complement.
And because this set is open, the complement is closed. Okay? So that's where we are with that, and I've got one more question here. Must every infinite set have a limit point? I guess we've done it today, haven't we? Right, and I've got a few little exercises for you. Some of these have been done in the text. There are these little clip signs that show help. Some of them are done, and some not. I'll probably spend a few minutes on this on Wednesday doing just some of these exercises. I do not intend to do all of them, but I think I will do maybe some of the harder ones. I'll then be introducing the topic of neighborhoods of infinity, which is a very small topic. Please don't move because your noise goes into the microphone. I want you to know that the section on neighborhoods of infinity is a very small section. You would be helping yourselves and me very greatly if you would take a forward glance today or Tuesday before Wednesday at the topic on neighborhoods of infinity so that we should not have to dilly-dally over there, okay? Will you please give that a bash? It's a very simple topic, and I'd like you to just look at it. I will be spending 5 minutes on it next time. Next time we will be beginning the next chapter, sequences. That's what I have to say, and I'm not